let's finish up talking about volumes of pyramids and cones today. We've talked about volumes of prisms and cylinders, and we saw how prisms and cylinders have a tremendous relationship when it comes to their areas, their area formulas. They also have a great relationship when it comes to volume. So if you can connect those relationships, it's much easier to remember those particular formulas. Likewise, our volumes of pyramids and cones, those pyramids and cones have a great relationship when it comes to volumes as they did with their lateral area and total surface area. So look at the connections, and that will help you tremendously to remember these formulas. So as we start off with the volume of a pyramid, let's start with the formula itself to find how much it takes to fill up a pyramid. And notice this doesn't say regular pyramid this time. It says just a volume of a pyramid. The volume is 1/3 the area of the base times the height of the pyramid. Now this time we're going to be using the altitude of the pyramid, not the slant height. So we're going to use that perpendicular from the vertex point to the base. That is the length that we're going to need now. So let's look at example 1 and see in action what we've got going here. Find the volume of the pyramid. As I look at my pyramid, it is a rectangular pyramid, or has a base. It's a rectangle, not a square this time. So uppercase B, again, is the area of our base. And since our base is a rectangle, we've got one of its bases times one of its heights, or 9.5 times 8. And if I multiply 9.5 times 8, then I'm going to get 76 units. So the area of my base is 76 units. Now, this height is not the same as this height, okay? This was for the base. This was the base times the height of just the base piece. This height means the height of the pyramid. So this height refers to this 9. So once I multiply and get my uppercase B, my 76, then I'm going to have 1/3 times the 76 times the height of the pyramid, which is really going to be just 76 times 3, isn't it? Because I can take the 1/3 of 9 quickly and in my head. And I get 228 cubic centimeters, since we're still talking about volume. Again, that uppercase B is all about finding the area of the base. That's all about Chapter 11. Now take a minute, stop the video, and let's do 1A and come back and check it together, okay? All right, 1A, they didn't tell me if I have a regular hexagon or not for my base, but I probably do. They did give me the entire area this time, so that was the sort of didn't challenge us as much as I would like for them to have. So my volume on 1A is, again, write that formula so you know what to focus on, what you know and what you need to find. The uppercase B this time is given to be 22. And again, the height is the height of the pyramid. So I'm going to multiply 22 times 5, and I'll divide that answer by 3. And I'm going to get 36 2/3 cubic centimeters. So if I have a little ice cube or a little sugar cube that's 1 centimeter cube, it would take me exactly 36 2/3 of those little cubes to fill up that particular pyramid in 1A. Let's do the same thing with 1B. The volume of 1B is still 1/3 the area of the base times the height. The base is a right triangle. And we seem to keep forgetting something that we talked about earlier in the year, but I want you to really, really make sure you get this. When the base is a right triangle and you're multiplying 1/2 the base times the height, this base and this height in a right triangle can always be the two legs that make the right angle. Now you can put some altitudes in there and try to work it a lot of more difficult ways, but why borrow that trouble and make things difficult? And you may even hit a dead end where you don't have enough information to solve. So when you have a right triangle and you're trying to find its area, your base and your height are always perpendicular to each other, and they can always be the two legs of the triangle that make the right angle. In other words, the two legs that are not the hypotenuse. So in this case, when I multiply these guys together, it looks like I'm going to get 45. Okay, let's see, that's 1/2 of 6 is 3. Yeah, it's going to be 45 square feet. But then when I multiply it by the 14 feet, that is the height, that's going to give me my cubic feet. So my 45 times the 14 divided by 3 is about 210, or equals, I guess, 210 cubic feet. Now what's really nice, again, as I started off the video, the cones and the pyramids, again, have that very close relationship. We still have 1/3 the base times the height for the volume of a cone, but every cone will have as its base a circle. So to be even more specific, I can say 1/3 pi r squared times the height of the cone. If you'll look down here at 2b, again, we're going to be using some trigonometric rules to help us find what's going on here. Now, as I look, I've got a 58-degree angle. So I'm going to use the tangent function. Tangent is opposite over adjacent, and I'm going to find that my radius is about 6.9 using trigonometry. Then by using that, I'm going to have to use that 6.9 as the radius of my circle, so that when I find my volume, and let the calculator carry the pi, my radius is 6.9 squared, and then I'll put in my height of 11. So using trigonometry, we were able to find the radius of our circle. So if we could just stop for a minute, let's look at 2a and see how you can do that one. And let's look at 2c. Let's just stop and see how you do. Now in 2c, this looks a little confusing to me. I believe what they mean for that 30-degree angle is to be this angle right here. That doesn't look very, it looks very confusing. So we're going to call that angle right there that I've marked the 30-degree angle. All right, again, write your formula. For 2a, the volume is 1/3 the base times the height, but my base is a circle. Let's fill in what we've got. The r is 3, and they give us the 7. So this is just a plug-in problem. So we're going to have 21 pi. That's an exact answer. Remember, when you leave the pi, that's exact. But if I multiply 21 times pi and I put in pi in my calculator instead of 3.14, I'll get a more accurate answer than if I had used the 3.14. I'm going to get 65.97 cubic feet. Cubic feet. Now remember, this is exact, this is rounded. So if I look at 2c, again, the volume is 1/3 pi r squared h. Let's see what we know and what we need to find. We don't know the radius. The height is given to be 5. So we've got to find the radius. Since I have a 30, 60, 90 here, it looks like my short leg is 30 degrees. This is way off scale if I have interpreted this the way they wanted it interpreted. But my 30-degree angle's across from the 5, so the 5 is the short leg. So that means that my long leg, which serves as the radius, is 5 on root 3. So up here, I'll put 5 on root 3. Now, instead of putting that in my calculator, since I'm squaring that, I'm going to make this as accurate as I can. 5 times 5 is 25, and root 3 times root 3 is 3. And the reason I did that was because I'm going to cancel those guys out. My most accurate answer is 125 pi cubic centimeters. But since they asked to the nearest inch, I'm going to 125 times pi. Again, not 3.14, but the entire pi symbol. And I'm going to get approximately 392.7 cubic centimeters. Here's one of the charts at the bottom of the page that you guys like, where they pull all the formulas together, and you can see how closely they're related. There's your volume of your prism and your volume of your cylinder, and then the volume of your pyramid and the volume of your cone, how closely they're related, so that you don't really have that much to memorize if you can make the connections. One more thing I wanted to talk about on the next page. Let me pull up a picture here. I want to talk about Euler's rule of geometry, and I want to come up with a pretty prism. We'll just use this cube. All right. Euler is the name of a mathematician. We want to pronounce it Euler, and I do hear a lot of mathematicians and professors that I've had use the word Euler instead of Euler, but I think it's really supposed to be pronounced Euler. Sometimes property, sometimes theorem or theory. We're just going to say Euler's theorem of geometry. Okay, after a lot of investigation and observation, Euler noticed that if you take the faces of any polygon, now in this case, remember our faces are flat surfaces. So in this one, we've got 1, 2, 3, and then we've got the one back behind there is 4, and the one back behind there is 5, and then we're sitting on one, that's 6. So this cube has 6 flat surfaces. So for its faces or flat surfaces, we have 6. The vertices are really just the corners. So in this case, let's make them in blue. We have 1, 2, 3, 4, 5, 6, 7, and then I've got one back here that you can't see. That would be 8. So I have 8 vertices. And then we want to see how many edges we have. Now, edges are going to be where two faces come together. So why don't I try another color here? Let's go with the yellow. Okay, so my edges are, there's 1, there's 2, 3, 4. Then I'd have 4 more on the bottom. 2 I can see and 2 I can't. So that'd be 8. And then you've got 9, 10, 11, and then 1 back there is 12. So I have 12 edges. One thing that Euler saw is that if you add the number of faces and the number of vertices, you will always get the number of edges plus 2. Okay, so let's see if that works here. My faces of the cube is 6. My vertices, we have 8. the edges have 12. The plus 2 is in the formula, so that gives me 14 equals 14. That is always true. That is Euler's theorem of geometry, that the number of faces of a prism plus the number of vertices will always equal to the number of edges plus 2.